Hi guys, welcome to another HSC Chemistry video in the acidic environment series. In the last one we looked at alcohols and alkanoic acids, and we did that deliberately so we could now examine esters and the process of esterification. So in this particular video we're going to be looking at esters and the reaction of an alcohol with an organic or carboxylic acid in the presence of sulfuric acid, concentrated sulfuric acid, which acts as a catalyst in order to produce an ester. So the esters in this case have a very complex name. They are called alkyl alkanoates. And effectively, they're like a salt that is formed in the reaction between an alcohol and a carboxylic or alkanoic acid. Once a water molecule has been removed and the sulfuric acid, the concentrated sulfuric acid, acts as a catalyst. In fact, it acts as a dehydrating agent. And this dehydrating agent takes the water out of these two combining molecules in order to form a single molecule, which is the ester. So here's an example, ethanoic acid, which looks like this. And in combination with methanol, which looks like this. And effectively what we're doing is if we used the acid on the basis of our Bronsted-Lowry, we would say it is a proton donor. So this hydrogen is going to be lost and it's going to combine with this OH group, and these two together are going to form the water molecule. What they leave is a bond here and here effectively, and that is where the ester links together. So you're actually going to see a carbon to oxygen to carbon bond. In actual fact, when they've traced these with radioactive traces, they found that sometimes it's actually the, let me just put this here, a little radioactive tracer on the oxygen that suggests that this oxygen is actually remaining in the ester, and it's the OH group from the acid that forms the water molecule, but that just confuses things. So let's store that in the brain and then form this ester. So the ester then is, if we start with the methyl bit here, we've got these three hydrogens that are still present. Then we've got this bond that we've said the OH group is going to disappear from, and it's going to link with the O, which links to the C, and the double bonded O from this part of the molecule of the acid. And then of course there is one more carbon on the end of that acid chain. So effectively, when we're looking at our ester, we've effectively got this here is the section that highlights or identifies this particular molecule as an ester. Now, the process of esterification is one that we will look at in the laboratory. In fact, it's one that we have already carried out in the laboratory. And it's very broadly just a reaction that involves an alcohol and an alkanoic acid reacting together in the presence of a catalyst in order to form an ester. One of the problems that we have with the esterification process is that it is slow. It forms an equilibrium, and as a consequence of that does not proceed to completion. This means that we need to be aware of some of the factors that we can use in order to speed up the rate of this particular reaction. And of course, heat is one of the important things that can be used to speed up the rate of a reaction, and likewise a catalyst. And in this case, when we're carrying out esterification, we're actually going to use both of these factors in order to increase the reaction rate and also our knowledge of equilibria in order to shift that equilibrium to favor the formation of the product, which is, in this case, the ester. The reason that we use sulfuric acid as a catalyst is because we want to increase the rate of the reaction. We want the rate of the reaction to be faster. It's too slow if we just let it carry on at room temperature. And the acid catalyst is going to absorb the water and drive the reaction towards the formation of the products. So therefore, if we have our alcohol plus our acid in equilibrium with our ester, what our catalyst does is it helps to drive the reaction quicker. Of course, it doesn't change the position of equilibrium. All it does is allows us to reach that final concentration of ester more quickly. There are some other things that we can do in order to try and favor the formation of the ester, and you'll see that when we talk a little bit later about refluxing. So if hexanoic acid and ethanol were mixed together under certain conditions to produce an ester, could you give the structural formula and the names of the products? Well, one of those products is going to be H2O or water, but the other is going to be an ester. The first part always comes from the alcohol. The alcohol supplies the first part of the name, so it's ethyl. And then the acid is going to form the anion component of the salt. So it's actually this part that's critical. So it's ethyl hexanoate is the name of the ester that's formed. If you then wanted to draw it, you would start with your 2 carbons, which from your alcohol. Then we've got our O group, then our C, double bond O, that's where our ester bond comes from, and then that carbon is part of the 6 carbons that are from the original acid. Whoops, just remove that for a second. There. Just remember to make sure that there are 4 bonds around each of the carbons. It does get a little bit messy when some of these are longer chains, but just have a little bit of practice drawing them and you'll get very, very good. It's a reaction that we're going to look at in class. If you haven't already done that, it's worth having a look at that. We made some very nice esters last time around, and we will look at the process of refluxing in a future video. Thanks for watching.